Well, see, in the last lecture, we have calculated work in a very specialized case when a gaseous product is produced in the chemical reaction. Now, another I am taking another example of very specialized case. See, when there is a phase change, so during phase change also we can calculate what work. So, what are the different, phase changes? So, all of you are knowing that the solid may convert into the liquid. See, this is one kind of phase change, and liquid to vapor phase change, and solid to vapor phase change, and solid to solid also phase change is observed when there is a change in the crystalline structure. So suppose that some solid, A solid is there, A solid, and its crystalline form, suppose that alpha, and it is converted into the same chemical species A and solid, but some other crystal structure beta, right? So solid to solid also phase change we can say. So this is the maximum kind of phase changes which you can observe in physical sciences. Solid to liquid, number one. Liquid to vapor, number two. Solid to vapor, number three. And number four, solid to solid. This is very less common, right? Very less common, because generally people are thinking, okay, this phase is basically solid, liquid and gas, right? They were thinking like that. Suppose that some example is given, like graphite to diamond, right? Carbon, graphite, graphite to diamond, carbon, diamond. So carbon graphite and carbon diamond both represents the different phases. See, what is the correct definition of phase? The correct definition of phase is phase throughout. A phase has the same properties. So graphite and diamond do not share the same properties. They have entirely different properties, although both are solid. So they represents the different phases. So this is an example of phase change, change of phase, and this solid to solid, one crystalline form to other crystalline form. So this is also included in the phase change. Means graphite and diamond both represents the different phases of carbon solid, right? So this is the scientific definition of phase. Don't be stick yourself that only solid, liquid and gas are the different phases, right? Suppose that if you have liquid crystals and two different types of liquids, liquid crystals are in equilibrium, then that is also qualify the definition of phase. But see, for all these phase changes, these two things are invariable. Means they are isothermal. All phase changes are isothermal and isobaric, right? Means T is constant. This equilibrium, this is a reversible process basically. All phase changes, so certain properties I am writing here for this phase change. So for phase change is a reversible process. T constant, T constant. It is defined under this condition. P constant means isobaric also, P constant. If T constant, then what is the heat capacity or specific heat? Specific heat whatsoever that is infinite, right? Specific heat in this situation is infinite. And see, T is constant, but delta E is not equal to 0. Means in phase change, temperature is constant, but there is some change in internal energy. Means when one phase is converted to another phase. That's why I have in the beginning I have told you that this is very special case, and everybody should focus here. So in phase change, delta E is not equal to 0, although temperature is constant. Delta H is not equal to 0. Delta S is also not equal to 0, but delta G is equal to 0. Delta G is equal to 0. So for any kind of phase change, these thermodynamic parameters are always what? Valid. Why this E is not equal to 0, H is not equal to 0, although they are defined at constant temperature. Temperature is constant, but when solid is converted into liquid, some in dissociation of some intermolecular forces is taking place. And why this is 0 for isothermal process? Because we are assuming that the behavior of the gas is ideal, and if the behavior of the gas is not ideal, then delta is not equal to 0, as I have shown you in the cases of real gases. So why this is not equal to 0? The answer is see, one more thing I will add here. Then after that, I will discuss this. Delta S of system and delta S of surrounding, because is also not equal to 0. But delta S total, this is 0. Delta S total is equal to 0. So here I am giving you the fact that internal energy is the function of system. This will tells about only system. H tells about only system, but delta S is always defined with respect to system and surrounding simultaneously. So the delta S total is 0, but delta S system and delta S surrounding is not equal to 0. Be careful. And delta G again the function of system only. So these functions are default for the system only, so they are represented like this. But entropy is defined with respect to system and surrounding both. That's why it is written like this. So delta S total is 0, but delta S system is not equal to 0, and delta S surrounding is not equal to 0. In many exams, you may get direct questions based on this, right? So why this delta H and delta E are not equal to 0? Why delta E and delta H are non-zero for phase changes? Phase change. So the answer is dissociation of intermolecular forces, because we can say potential energy is not 0 here, because potential energy is not equal to 0. That is, have interaction between molecules. So if there is a interaction between the molecules, H2O liquid, suppose that we have taken H2O as example. So H2O liquid and H2O vapor. So if there is a cleavage of intermolecular forces, so definitely, although temperature is constant, but there is some change in what internal energy, right? So you can say heat capacity will change from liquid to solid or from liquid to vapor. Means H2O liquid and H2O vapor have different heat capacities, because in heat capacities what different motions were contributing. So since here major contribution is coming from this potential energy in the case of solid, in the case of liquid, you always have this potential energy, but in case of ideal gas there is no potential energy. So this is the reason why we are not uh, taking this delta E and delta H is equal to 0 for phase change, right? Similarly, for chemical reaction, delta E and delta H are non-zero even temperature is constant, because in chemical reactions, one type of molecule is converted into other type of molecule, means total degree of freedom is changing in that case. So in that case, also delta H and delta E are not equal to 0 even temperature is constant, right? So this is phase change. So for any kind of phase change, you can calculate the work. Again, I am telling you the same formula. The work delta W reversible, because all phase changes are reversible in nature. That is equal to minus P external. This is constant 122 dB. Right. This is the master formula, and by using this formula, you can calculate what work involved in this process, right? So you just evaluate by any formula that delta V means change in volume. If you are able to evaluate change in volume, you can very easily calculate this work, right? And pressure is constant, so your delta H is equal to delta Q heat change at this constant pressure. This you can use, and work you can calculate from here. PdV work you have calculated from here. If you want to calculate delta E, so you have relation delta H is equal to delta E plus delta PV, right? So this equation you can use, and since it is a constant pressure situation, so you can write here P delta V, basically P delta V. So this is equal to expansion work, so you can calculate work from here, you can put here and see yes, you can put here this work and get the delta E, value of delta E. So by using these equations, you can very easily calculate the work and heat change, internal energy change, and enthalpy change during the phase changes, right? Now see one example I am giving you. Suppose that process is given 1 mole H2O liquid to 1 mole H2O vapor at which 373 100 degrees Celsius at 100 degrees Celsius, right? And 1 ATM or 1 bar, you can say, right? And what the other parameters given, delta H is equal to 406 406 for this process. Delta H is equal to 40668 40668.48 joules per mole, right? So this is given, and density of H2O liquid is given at this, in this situation, 0.9573, 0.9573 kilograms per meter cube, and volume of H water vapor in this situation is 30.2, 30.2 dm cube, right? So find, this information is given, find delta E, delta Q, right? And work, WP. So see, 1 mole water liquid converted into 1 mole of water vapor at 100 degrees Celsius and 1 atm. This is the condition of the conversion of liquid water into vapor. Delta H for this process is given, molar enthalpy change, and you can say this is what. So see the answer, how to proceed this question. This delta H bar, you can say this is vaporization process. So delta H vaporization, it is given, and this is equal to, we can write 40.6, 40.6 kilojoules per mole, kilojoules per mole. So it is given here, and you know pressure is constant, 1 atm. So when pressure is constant, so you can write delta H bar is equal to delta Q at constant pressure. So this is equal to 40.6 kilojoule per mole. Not required, calculation is not required. Q you have calculated. Now if you are able to calculate W, so by using first law of thermodynamics you can calculate this, or if you are able to calculate W, then delta H is equal to delta E plus PV, you can calculate this delta E, right? So see how to calculate work. So work WPV here in this phase change is equal to minus P external, and volume of vapor, water vapor, minus volume of H2O liquid. So in the question it is given, volume of water vapor. You just calculate water volume of water liquid. So volume of water liquid, so you can use density of water is equal to mass of water by volume of water. So this is equation 2. You can use this equation to calculate volume. So volume of water is equal to mass of water. What is 1 mole we have taken? So 1 mole means 18 gram divided by, now see WPV is equal to minus 1 atm. Volume of water liquid, what this, 0.0188 dm cube minus oh, 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 30.2 30.2 dm cube per mole minus 0.0188 dm cube, right? So this is equal to minus 30. This is what 0.01. So 30.00. This is dm cube or liter. You can write liter into atm, right? So convert this liter into atm into joules. So this is very simple. Minus 30.00 multiply with r and divide with r, liter atm, right? This liter atm. So and take here the unit of magnitude of r in joules. So 30.00 multiplied by r. So here I have taken 8.314 joules per mole per degree Kelvin into this liter atm, 30 liter atm, and take divide with that value of r which is in liter atm. So 0.0821 liter atm per mole per degree Kelvin. So see, per mole per degree Kelvin, atm, liter cancel. So we will get joules. So minus 30 multiplied by 101.325 joules. Division of this is 101.2. So remember 101 basically 101.2, right? So 30 multiplied by 101.2. So this is 3036. So this is equal to minus 3036 joules, right? So work is equal to this. So delta E is equal to delta E is equal to delta Q plus delta W. Delta Q is how much? Delta Q is given 40.40668 minus 3036, right? So 3036. So this is equal to 37608 0.4 joules. Don't write this 0.4. So 37 40668 minus 3036 37632 37632 joules, right? So this is the delta E, and this is the delta work, right? And this is delta H and delta Q, right? So we have calculated all the parameters for this evaporation of 1 mole of water at 100 degrees Celsius and 1 atm pressure, right? Okay, so see this adiabatic process. This is the last part of thermodynamics first law, application of thermodynamics first law. So how to calculate internal energy change, work, and enthalpy change in adiabatic process. See, adiabatic process, for adiabatic process, this is always true that there is no heat change, no heat change, heat change, no heat change between system and surrounding, between system and surrounding. Means there is no heat change between system and surrounding. So such type of process is called adiabatic process. For adiabatic process, this is always true, always. So if a gas is expanding or under compression is there in adiabatic process, one thermodynamic parameter that is always true, that this delta Q is equal to 0. So what is the impact of this? The impact of this, that temperature of gas is also, will change. Because when delta Q is not equal to 0, means when heat energy can flow between system and surrounding easily. So in that situation, this heat will maintain the temperature. So isothermal process we can easily achieve. But here, this adiabatic process, there is no temperature constant. Means whenever process is going on, the temperature will change. The temperature will change, right? But uh, this temperature change affects the, rate of pressure change compared to the isothermal process. In isothermal process, when gas is expanding, there is a change in the pressure. So if you compare isothermal process with the adiabatic process, the rate of change of pressure is more in case of adiabatic process compared to the isothermal process, and that will reflect, in terms of equation, and in terms of in terms of equation we can calculate this, right? So I am considering first case, reversible adiabatic expansion or compression. So suppose that we have 1 mole of gas, and initial condition I have taken, volume is V1 and temperature is T1, and it is undergoing some expansion or compression, whatsoever, expansion or compression, right? So this is another state, 1 mole gas, V2 and T2, right? And delta Q is equal to 0, and the process is reversible. I am taking this process is reversible, right? So you can argue why you have not considered this pressure. You can consider pressure and temperature. You can consider here pressure and volume, right? Pressure is also varying here, but as per the convention, I have not written that. Pressure is also changing. When a gas is expanding, the pressure of the system will change, obviously. So here all three variables simultaneously changing, pressure, volume. But if at any moment of time we want, we can calculate that. So here we try to always express the state in terms of two variables. Although pressure is changing, remember, when a gas is expanding, volume is changing, pressure is changing, and there is no heat change between system and surrounding, so temperature is also changing. So this delta Q is equal to 0. This temperature change, basically the consequence of delta Q is equal to 0. So in adiabatic process, we can express this path. We can design this path, right? How? All of you are knowing that when two variables are changing, you have to consider like this. So this is a method of expression. Basically, you can express any way. You can take PV here, P1 V1, P2 V2, and temperature is also changing, but not required to write all three variables to explain explain this process, because moles is constant. So now three variables are there. You have specified two, those third automatically will calculated by PV is equal to nRT, no problem. So see, I am taking here, this is a temperature T, and here this is V. As per my path designing. So I am designing here path. You can see I will carefully see. Suppose that this is reversible path. So one state is here, one state is here, another state is here, right? So this is V final, and this is V initial, right? V initial. Okay, this is V initial, this is V final. So now see, and this is T initial, T initial, and this is T final. So this is adiabatic expansion. I am showing here V. V final is more than V2 is more than V1. So we can say this is an expansion. If path is this, we are moving in this way. So this is an expansion. So how to move, how to design, how to achieve this path, and how to explain this. So see, when you can take a step like this, this is a constant temperature, constant temperature. So T constant from here to here, and after that, this V is constant, and T is changing. So basically here from this point to this point, this is some intermediate state. This is step 1. So what is changing here? The volume is changing, and delta Q is 0. So basically here we can say that temperature is constant. Constant means internal energy E is constant. E constant, and here this is step 2. So this is step 1, and this is step 2. here internal energy is changing. So internal energy is changing by which formula? You can write delta E is equal to CV delta T. Means this is the T final and this is the T initial. So here work is 0. Here work is 0 from here to here, right? So we can write here that work, PV work is 0. WPV is equal to 0, right? And internal energy change is there. Here volume is changing, but internal energy is what? Constant. We cannot say that, this is 0. E is constant, delta E is 0, you can say, because temperature is constant. So E is constant, but delta E, you can write delta E is equal to 0. But here, this time, the work is non-zero. WPV is non-zero. And these two, this and this, are always equal. So basically this is the path designing of from this state to this state, and this what I have shown here, this is what isothermal path, we can say. Or adiabatic path also the same. Shape will be the same. The slope is different for isothermal and adiabatic process. So this what I have written here, that I have shown you on this graph. So this is the characteristic feature of this adiabatic expansion or compression. This is called path designing, and path designing is very important. First, you take one variable constant, then you take other variable constant, and then you can design the path, right? So this is the way to achieve this process. Now in the reversible process, as this delta Q is equal to 0, so you can write delta E is equal to delta WPV, and this is very what important equation. Although I have written here, see, this is here delta E, you can write NCV delta T, because temperature is changing here, is equal to, this is a reversible process I have initially written, so minus P gas into T, right? Remember, in the reversible process, all of you are knowing that P external is equal to P gas plus minus dP, and dP tends to 0. So this WPV minus is the convention, and P gas, it is variable here in the reversible process. So infinitely small steps we are moving here. So now you can see this is the internal energy change and PV work are equal, as delta Q is equal to 0, always in adiabatic process. So first law of thermodynamics will give you this relation. Now from this you can calculate final temperature of the gas. What is the final temperature? How much work is involved? Work is always equal to NCV delta T, right? So if you are able to find out final temperature, final pressure, all these things, then you can very easily calculate work. Otherwise you cannot calculate work, because this work is always equal to NCV delta T in adiabatic process, right? Now see, very easily we can calculate. Apply your formula. 1 to 2 initial to final state. 1 to 2 initial to final. We are assuming that this CV is independent of changing temperature. Although assuming, not this is not the truth, but we are assuming that CV is independent of what? Temperature. So here we can no, wait. We can replace this P gas with nRT dV by V 1 to 2 and NCV delta T. Right, like this. P gas is equal to nRT by V. Although T is not constant here, so take T this side. So you can write NCV delta T by T is equal to minus N R 1 to 2 dV by V 1 to 2. Temperature change and volume change. Now this N and N is cancelled. So we can write here CV ln T2 by T1 is equal to minus R ln V2 by V1. So remove this minus sign, so you can write here R ln V1 by V2 CV ln T2 by T1. Right? We can write very easily. Now we can write here that this anti-log of this equation, anti-log. So what we get? T2 by T1 to the power CV is equal to V1 by V2 to the power R. So T2 by T1, T2 by T1 is equal to V1 by V2 to the power R by CV, right? R by CV. So R by CV is equal to, we can write this gamma minus 1. So here we can write V1 by V2 to the power gamma minus 1 T2 by T1. So by using this equation, we can calculate, this is equation 2, final temperature. If initial temperature, initial volume, final volume is given, then by using this you can calculate what? Final temperature, right? And all of you are knowing what is this gamma? Gamma is equal to Cp by Cv, right? So gamma is equal to Cp by Cv, all of you are knowing. So similarly, we can calculate final pressure also in the reversible adiabatic process. So this is the calculation of temperature, by using this equation. Calculation of temperature, final temperature in adiabatic reversible process, right? Now you can calculate other variables as well. How? P1 V1 by T1 is equal to P2 V2 by T2. So T2 by T1 is equal to, you can write from this equation 2, P2 V2 by P1 V1 is equal to V1 to the power gamma minus 1 by V2 to the power gamma minus 1. So you can write here P2 V2 to the power gamma minus 1 into V2 is equal to P1 V1 into V1 to the power gamma minus 1. So you can write here P2 V2 to the power gamma is equal to P1 V1 to the power gamma. So from this equation you can calculate the final pressure if initial pressure and initial final volume is given, right? Or you can say PV to the power gamma is equal to constant. So this is adiabatic process. And what is isothermal process? Isothermal process is what? PV is equal to constant. And here PV to the power gamma is equal to constant. So this is the difference between isothermal and adiabatic process. So this is adiabatic process and isothermal process. PV is equal to K dash. So this is the difference, right? So this gamma times difference is there in their slope. If you take P versus V plot, so the slope of adiabate is gamma times of the slope of isotherm, right? So the slope of adiabate is minus of gamma times of the slope of isotherm, because in case of adiabatic process pressure is more steeply decreased compared to the isotherm, because temperature is also falling in the case of expansion, right? So these are the different temperature, pressure, volume you can calculate in case of what isothermal sorry, in the case of reversible adiabatic expansion. Now what is work? So work in adiabatic process, W adiabatic is equal to delta E, and delta E is equal to NCV delta T, or you can write NCV T2 minus T1. So this is the work. Adiabatic, this is equation 6, the reversible adiabatic. Reversible adiabatic. And delta E is same. What is delta H? Delta H, it is a state function, so you can directly use this delta T. So now you have calculated all the variables in the reversible adiabatic process. How to find the temperature, final pressure? You have this formula. By using this formula you can calculate final temperature, final pressure, right? So this is adiabatic reversible process. Now see, when you take adiabatic irreversible process, so when we take adiabatic irreversible process, see, irreversible, right? Adiabatic expansion. So in case of irreversible process, see, delta Q is equal to 0, and again delta E irreversible is equal to irreversible. So you can argue with me that in both the cases delta E. So what is the difference here? The difference is lie here, dear students. Remember, temperature means when you are moving reversibly and irreversibly, you won't get the final temperature same. In both the cases, final temperature will be the different. So these two are different, right? So in this case, irreversible process, the expansion is always against constant external pressure. So P external dV, and here NCV delta T, your equation will integrate here only because external pressure is constant. So in this way you can calculate the final temperature, because in both the cases final temperature, final pressure will not be the same, right? So here you will get NCV T2 minus T1 is equal to minus P external V2 minus V1. By using this equation, you can calculate the final temperature of the gas if initial temperature and volume is given. So simple. No, there is no gamma here. See, you are calculating final temperature in reversible process by using this equation, and in irreversible process you are calculating final temperature by using this equation. And what about pressure? If you want, you can calculate the pressure as well, minus P external, and here you can use equation of state nRT2 by P2 minus nRT1 by P1. So if pressure is given, then you can use equation 3, this NCV minus T1. So these two equations you have, through which you can calculate final pressure, initial pressure, final temperature, initial temperature, if all other variables are known. Right? No problem. So delta E is equal to NCV T2 minus T1, and this is the formula you can use to calculate internal energy, and this is also equal to the work W irreversible. So what is the difference? There is no difference in the formula, but there is a difference in temperature. So here, to differentiate T irreversible and T1 irreversible. And remember, T2 irreversible is never be equal to the T2 reversible, because in both the cases there is a loss in internal energy is different, because work is different. So different work, different loss in temperature, so different final state, right? So suppose that, and what about delta H? Delta H is equal to again NCP delta T, and this time also T2 irreversible minus T1 irreversible. So basically you have to calculate delta H by using the same equation, but temperature, to calculate the temperature by different equations. Here in irreversible process you have to calculate by this equation, and in case of reversible process you can calculate by that. So this is the calculation of delta H, delta E, work in reversible adiabatic and irreversible adiabatic. Now see, suppose that there is expansion of an ideal gas. Ideal gas, right? So what? See, W reversible is more than the W irreversible. It is true always. If W reversible is more than the this irreversible, then temperature, loss in internal energy in which case more, because whatever the work is doing by work is done by the gas, that energy is coming from internal energy. So the loss of internal energy, so you can say delta E reversible is less than delta E irreversible. So final temperature in case of reversible is less compared to the in case of reversible is less than irreversible. So you can say that the T2 irreversible is more than the T2 reversible. Hopefully all of you are getting this point. This is very important point, and you can get the question directly based on this. When gas is expanding, there is no heat change between system and surrounding. In the reversible expansion, more work is done by the gas, and for doing this work, energy is coming from internal energy. So there is a loss of temperature is more in case of reversible process, because more work is extracted from the system. So loss in energy is more in case of reversible. So T2 reversible is less than T2 irreversible in case of expansion. Suppose that compression is taking place. Compression of an ideal gas. So this time W reversible is less than W irreversible. Means this time, and expansion, so cooling takes place. Cooling takes place. Means gas will cool down. And compression, in case of compression, temperature will rise, means gas will becomes warm, right? So warming, in this case temperature is rising, so warming takes place. So delta E reversible is more more than delta E irreversible, because this time in the case of irreversible, the more work has to be done on the system. So final, so see this, the same delta E irreversible is more than this, and temperature also had the same relation T2 reversible, right? So T2 irreversible is always more than T2 reversible, whether it is compression or this is expansion. So here heating takes place, right? So in this case, in the case of irreversible process, more work has to be done on the system, more heating will take place, means internal energy change is more. So this time in internal energy change is more here, and this time the internal energy change is more in case of because there is a cooling, and here this is a heating. So these two are very important generalization, and this you have to I will careful whenever you are answering the gas expansion is taking place or compression is taking place, right? So in the next class we will do some problems based on this, and after that this first law of thermodynamics will be over. After that we will start thermochemistry, and then second law and third law accordingly.